Good morning, ladies and gentlemen. Welcome to optics, EMR optics of convex thin lenses. Here we have an optical bench, a candle on a meter stick. Now there's 2 meter sticks, just don't worry about that. That's just so I can have the candle steady so it doesn't fall over and set everything on fire, which kind of sucks. So here I have my screen set at 50 centimeters. There we go, from the candle, okay? Now, here, the candle is the object. The image appears on the screen over here. So if I put my lens in between, and you can start to see an image being formed here. Just tilt that down a smidge. Oh, sorry, of course I can't have my hand in the way, which sucks. Now, the lab says fix the candle onto one of the attachment brackets, done. That's the light source, this is the object. Number 2, fit the concave lens onto another bracket. Place the lens on the optical bench. There it is. Fix the screen onto the bench. Screen, and there's your image there. Now the image is not in focus, so slide the screen to a distance of 50 centimeters from the light source. Turn on the light and adjust it until the image of the candle is clearly visible on the screen. So it's backwards and forwards. You can go. I go right about there. Now note the image. If you look closely at that, let me look at my computer screen so I can clearly see that. Okay. Now the computer screen is a little hard to see, but if you look, no, actually it's not. You can see the top of the candle there, and you can see the flame upside down. You look very closely at the center of the flame. You can see the wick. So the image is inverted, real, and I'll tell you a secret, it's smaller. Okay? Now, note the characteristics: large, diminished, direct, inverted, recorded on the data table. Measure the height of the object and the height of the image. Okay, so record the data for you guys, so you don't actually have to do this lab. Anyway, now, 50 centimeters. Distance to the object. Let me see. The lens here, in this instance, is at 34 centimeters. All right. So, let me see. Distance to the object is 34. Distance to the image is 50 minus 34, which is 16. Height of the object. Now, a little hard to measure a burning flame with a plastic ruler. So I'm going to grab a wooden ruler and give it a try. Let's see. Yeah, this should get interesting. What's the worst that can happen? Okay, so I'm going to say the height of the image, the height of the object is, I'm going to call that 3.1 centimeters. Height of the image is, calling that about 1.5. Now, doing this all over again, moving to 60 centimeters. Notice choosing nice round numbers to keep the math simple. There we go. Move the lens, and you see what's happening to the image. It's getting clearer and clearer and clearer, and I'm going right there. So, 60 centimeters. Distance to the object is 44, 45, call it 45, keep the math simple. So that makes the distance to the image is 15. Height of the object will still be 3.1. Height of the image, I'm going to say 1.4. Now, I admit the image is hard to measure, but anyway. Now move this to 70 centimeters, and you can see once again the image is not as clear as it could be, so move that down a little bit. So slide that over, and you see the image, and then you're going, say, right there. So it's 70 centimeters. Distance to the image, object is 56.5. Which makes that 13.5 centimeters distance to the image. Now the height of the image is definitely smaller. Trying to measure that. I'm going to call that 1 centimeter. Now I'm looking at the height of my object at trial 2, 60 centimeters doesn't quite work. So, well, it looks different. So I'm going to double check that one because honestly, just double check that. No, that number seems to be a little different. So, and once again, trying to measure that. Now, of course, you guys have the advantage. Yeah, 1.4. You guys have the advantage because you actually have a much better view of this. Now, that is your basic optical bench lab. You've got distance to the object, candle to the lens. I'm not showing you the candle because that's really bright and it screws up the focus on the camera. But you also have distance to the image from the lens to the screen itself. Now, looking at the lab, it goes, the focal length of a lens can be determined from the equation 1 over f equals 1 over di plus 1 over dl. Using the data collected in the lab, determine the focal length of the lens in each trial. Show the average of these three. Yes, you do all the calculations on a separate sheet of paper. Show me the averages here, okay? So you get a focal length for 50 centimeters, a focal length from the 60 centimeter trial, and a focal length from the 70 centimeter triangle. They should be relatively close. Show me the average. Now, all right. So you could try cramming in all three sets of calculations in the average. Do one calculation, one good calculation here, then show me the three numbers and the average for them, okay? Now the magnification of the factor of the lens can be determined using the equation hi-ho equals minus dido. Using the data collected in the lab, determine the magnification factor of the lens in each trial. Show the average of these three. So do the magnification calculation for all three trials. Really, I don't need to see all three. You guys are showing me you're smart. Show me the calculation, nice, all steps for one of them. Then show me the answers for all three and show me the average of them, okay? And once again, this high HI is a little iffy. So I would use distance to image, distance to object. That's probably the better way to do it. Anyway, give it a try. Just take a picture of your work and submit it to me. Any questions, email me. Good luck.